Hello, everybody. Thanks for joining us this morning. We're here to talk about compression fittings and tube bending. We're going to leave the cameras on here just for a second while we all wave to you. Ron Cumlander is here to make this thing an exciting topic. And based on what we saw yesterday, he's going to do just that. So we're going to go ahead and turn off the cameras and get started. So thanks again. Again, compression fittings, tube bending. We have DK-LOK here with us today to talk about it. So if you look around the room, we've got a bunch of folks from a bunch of industries all over the country, and notably all four corners of the US are covered here this week. Again, briefly, Peerless opened in 1914 as a general mill supply company. And of course, we had to evolve with the times. We are ISO certified now. We've become a trusted source for process components. We operate under three distinct divisions: our Peerless process group, which really works with the plant environment, helping plants run smoothly and efficiently, always with a focus on better, safer, faster, cheaper. We have our ProCore division, where we have a team of engineers that work with our OEM customers on very challenging projects that have many layers of specifications. And finally, we have our high temp fabrication division, where we do a lot of scientific surfaces, laboratory casework, and high temperature installation. So our presenters, again, you saw Ron in the opening. Ron Cumlander is the Executive Vice President of DK-LOK USA. We also have Andy Galuli, who's having a little bit of technical difficulties, but we're sure he's going to be joining us shortly as well. From the Peerless side, we have the usual suspects: Dan Morgan, Greg Barrel, and me, Kevin Renaud. So as you know, this is the time when I basically humanize the presenter. Ron either didn't care to or forgot to send me any information about himself, nor did he send me a headshot. So I had to scour the internet, find anything I could find about him. So the only thing I could find was either this headshot, which is grainy, or the mug shot. So I chose this one. So speaking of mug shots, Dan Morgan, you want to take it away here to talk to the group about the operating system here today?
Yes, thank you, Kevin, and thanks again to everyone for being here. I am just going to go through a couple of housekeeping items here quickly to introduce you all to the control panel that's in front of you right now. So what you're looking at here, so a few of the controls, if you ever want to collapse this control panel, you can use this orange button right here. You can toggle between full screen and compressed mode. If you want to have a question, if you need some assistance with anything, you can click this raise hand button, and I can chat with you and try to resolve any issues you're having. Audio settings can be found here. And then most importantly, right here is the questions panel. So we obviously want this presentation to be as meaningful as possible to you. So as Ron is going through his presentation, if you have any questions at all about what he's covering, or something that's maybe application specific to you that you want answered, please feel free to write in questions, and that's what I'll be doing. I'll be taking a look, keeping an eye on any questions that are submitted, and I'll make sure to interject into Ron's presentation those questions that you send to us to make sure we get an answer for you. So, and then if you do end up asking us any questions, at the end of the webinar or at any time during the webinar, you can click File, Save Questions Chat Log, and then you can export the question chat log for your for future reference. So, yeah, with that, I'm gonna now turn this back over to Ron, and he's gonna get us going.
Okay, here we go. Thank you for your time, and thank you for being in attendance today, and we'll get started right off the bat. I do apologize for not having provided Kevin a better mug shot there. Actually, I serve as Executive Vice President at DK-LOK here, and also handle their technical issues. And so hopefully the information that I present to you today will be beneficial to you. There's a world of information for this type of product. As far as the things that we're going to be covering today. So this is the basics. And so feel free certainly to send your questions in to Dan, and we'll try to address those as we go through here. The itinerary for today's meeting is why use tubing, proper tube selection, proper tube handling, proper tube prep, proper fitting installation, proper fitting disassembly and remake, safety precautions, and basic tube measurement and bending. There are two types of instrumentation fittings out there on the market that are prevalent. That would be both a single ferrule design, as you see on the right-hand side, and then the two ferrule design, as you see on the left-hand side. Both of these designs are available in 1/16 of an inch OD through 2-inch OD, and also the metric comparables of 2 millimeter through 50. They, in the appropriate alloy materials, are heat code traceable. They are reusable from the standpoint you can disconnect and reconnect the connections once they've been made up initially. Some of them present a gaugeable feature, and most manufacturers roll their male threads on their connectors for strength rather than actually machining them, especially in the 1-inch and under sizes. Many manufacturers today provide their ferrules with some type of hardening process. Some of them have a hardening process that maintains the natural corrosion characteristics of the base metal. And there are others that still use hardening processes that do present some carburized material and subjected in certain applications, such as salt spray or maybe even some Clorox bleach type entities. There could be some corrosion in those areas due to the degradation of the stainless characteristics of the metal. So again, that's basically what we have as far as these designs that are out there in the market. More specifically, the two ferrule design is a geometric design. What you see here is the 4 components exploded in a male connector. And there are specific angles for the particular parts because the geometric design two ferrule fitting, all of these components are machined and designed to work together, just like the stem tip of a valve and the seat of a valve work together for complete shutoff. And so we'll talk about that a little bit more as we go through this presentation here. In the installed position, the two ferrule design provides a live loaded connection that compensates for vibration and temperature change, which are the two main causes of leakage in any installation environment that tube fittings will be subjected to. The single ferrule design is only a 3-piece component here. And one of the reasons the nut is black is because it was found by the brand that made the single ferrule more prevalent back in the day was Parker Hannifin. This would be their CPI brand fitting. They found that a moly-coated nut tended to do a better job of reducing the torque during the pull-up. So that's why you see a black nut on the single ferrule here in some of my photographs, is for that particular reason. Most manufacturers that do supply a single ferrule do offer the option of an all stainless nut because a lot of customers from a cosmetic standpoint just don't like the black nut. So you can have either option there. A lot of people ask us, what is the difference between single ferrule and two ferrule? And so I'll explain that by explaining how the single ferrule design works right here. It works by shear deformation. As you tighten the nut drives the single ferrule leading edge into the body bevel of the body of the fitting. And just by sheer force and deformation, the leading edge of the front ferrule of the single ferrule is forced to deform to match the contour of the body bevel of the fitting port itself. And so it works much like a cork being forced into the mouth of a wine bottle. The cork simply contours to the mouth of the wine bottle for a seal, and that is simply very similar to how the single ferrule design tube fitting works. The two ferrule design is much different. When these parts are finger tight, the way that the fitting works is when you insert the tube in tight against the shoulder, just as you would with the single ferrule. As you tighten the nut drives the back ferrule into the back of the front ferrule, which drives it into the body bevel, and through the tightening of the nut, pushes the front ferrule down the body bevel. And because it has a long, thin, tapered leading edge on the front ferrule, the deformation is minimal. And there's only a slight difference in angle between the body bevel and the front ferrule. So it's made to work. And then once the front ferrule's forward movement is retarded or actually stopped by being wedged between the body port and the OD of the tube, Then the back ferrule honors its leading edge angle and the angle machined into the back of the front ferrule, and it dives inward onto the tube at a 45-degree angle to deliver maximum bite depth to seal against high pressure gas and to provide the grip against blowout. So the two ferrules work together very well, and in the installed position at 1 1/4 turns, it is a very live loaded position because the back ferrule lifts the front ferrule out into a complete sealing position against the body bevel itself.
Hey, Ron.
Yes, sir.
Hey, just a reminder, you may want to use the laser pointer feature while talking about some of these if you want to just point out anything while you're going through this. You got it. Thank you.
Okay, I'll keep this down in the right-hand corner. Most manufacturers out there, especially for the two ferrule design, because of the controlled pull-up, the parts are predictable because of their dimensions and their tolerances and the travel on the threads. Use gap inspection gauges as a way for the installer to check for proper tightening. So this is an example of a gap inspection gauge here. It's typically referred to as a no-go gauge, and we'll talk about that a little bit further along as we go as well. In this photograph here, what you have is a union in the two ferrule design, and the left side of the union depicts thin wall tubing that has been installed 1 1/4 turns. Let's just say this is a 1/2 inch union. So that would be representative of 035 wall tubing. On the right-hand side, excuse me, you'll see an example in this union of maximum wall thickness tube in 1/2 inch, which would be representative of 083. And you can see there's a difference in the behavior of the tube and the ferrules as well. On the left side, the thin wall tube yields extremely to the bar stock ferrules during their fully swaged process at 1 1/4 turns. On the right-hand side, you can see that the tube does not yield as much, and there's only really one swage ring on the ID of the tube. That's at the leading edge of the front ferrule due to its wedging action. And the front ferrule actually does not travel quite as far down the body bevel as the one on the left because it's getting more resistance from the heavier tube wall. So we're still tightening the nut on both of these connections 1 1/4 turns, irregardless of the wall thickness of the tube. So when the front ferrule stops a little bit sooner because of the resistance in the heavier tube, and we're still going 1 1/4 turns, something has to absorb that change in travel, and the back ferrule does that. The back ferrule will receive that change in travel from the front ferrule by simply bowing or squatting as the nut continues to drive it forward to the 1 1/4 turn position. So the installation procedure does not change for the various wall thicknesses that are available for any specific OD. Here's a 1/4 turn presentation that explains exactly what takes place in the two ferrule design. Top left over here, you have the finger tight position where the tube is bottomed against the shoulder. The ferrules are in perfect alignment, and we're ready to start tightening the fitting. So by making a 1/4 turn on the nut with a wrench, what that does is the nut drives the back ferrule forward, which drives the front ferrule forward, and makes the initial contact on the body bevel and forces the leading edge of the front ferrule down onto the OD of the tube. So what we want to do through the pull-up is we want to close the gap between the body bevel and the front ferrule, and we want to maximize this sealing area as much as possible. So through another 1/2 turn on the nut, again, we're continuing to force the front ferrule down the body bevel and onto the OD of the tube. And at the 1/2 turn, if we were to be able to disassemble this and take a look at it, the back ferrule is not even attached to the tube at this point. It's simply acting as a bearing disc or a thrust washer to take the torque out of the pull-up and to push the front ferrule forward. At 3/4 of a turn, again, we're continuing to move the front ferrule down. Let's see, this is 3/4, I apologize. We continue to move the front ferrule down, and about 3/4 of a turn based on the wall thickness of the tube is about the time during the pull-up that the front ferrule starts to really stop its forward movement because it's being wedged between the OD of the tube and the body port. And about 3/4 of a turn is when the back ferrule then starts to say, hey, this guy in front of me is stopped, but this guy behind me is still coming forward. I have to go somewhere. So it honors this angle at its leading edge, and it dives inward onto the tube to deliver bite depth and grip and lift the front ferrule out into a sealing position. So here we are at the 1/4 turn pull-up. Both ferrules now are in contact with the OD of the tube. And because the front ferrule is sliding down this body bevel, so to speak, as it was coming down from the finger tight position, the two surfaces, the body port and the front ferrule, are basically polishing themselves, and that polishing enhances sealing capability. So again, 1 1/4 turns is the proper installation for all manufacturers on the market. So we need to complete that, and that last 1/4 turn is what really delivers the bite depth and the grip of the back ferrule into the OD of the tube, drives it under the front ferrule to lift it outward in a live loaded position against the body port. So that's basically what takes place during the pull-up of the 2 ferrule design fitting. Here's a cutaway of the single ferrule design. And so you can see again on the left side, this is thin wall. You can see that the tube yields tremendously to the leading edge of the single ferrule. And then over here is heavy wall. And again, if this is 1/2 inch, we're talking 0.35 versus 0.83. And you can see that the deformation and the shape of the single ferrule changes. Over here, there's still an arc in the single ferrule itself to the point that the nose is actually going inward onto the tube, and you see the yield of the tube. Over here, it looks like the ferrule is kind of flattened and straightened out, much like the front ferrule of a 2 ferrule design, because this tube wall is so heavy, it's giving much more resistance, and it just basically stops the forward movement quicker and kind of flattens out that arc in the single ferrule. So that's the difference between the 2 ferrule and the single ferrule design. They both can be used on various wall thicknesses, but by far, the 2 ferrule design is the most prevalent and the most dominant preferred design in the field globally today. Here's a tube working pressure chart that is in every manufacturer's catalog. On the left, you'll see the OD sizes from 1/16 of an inch through 2 inch. Across the top, you'll see the various wall thicknesses available on the market. And everywhere that the manufacturer prints a working pressure, that means that that particular OD and wall thickness combination is suitable to be used with that manufacturer's brand fitting. So once you get to 3/8 and above, even in 1/4 inch, you can see that there's at least 3, 4 or more wall thicknesses that the end user can choose from based on the working pressure requirements of their system. Now, one thing I do want to point out here is there's a shaded area in this chart, and the purpose for the shaded area is simply this. When using compression fittings in high pressure gas service, and it's up to the customer to determine if 500 PSI is high pressure to them, or if 3,500 PSI is high pressure to them, fitting manufacturers recommend for gas service that you use an OD and wall thickness combination that is outside the shaded area. And the reason for that goes back to the cutaway slides I showed previously, is that the heavier the tube wall, the more resistance the ferrules get, and the more resistance the ferrules get, the more work they can do on the OD of the tube to point out any imperfections such as scratches or things of that nature to ensure leak-tight performance. So again, as you can see, there's a myriad of wall thicknesses in the different sizes here that you can choose from based on what your system requirements may be. Special adapters that make the job easier in fabricating a tube system. This right here is a tube cap, and this particular part, along with its counterpart, gets confused many times, and I'll explain why. But in tube vernacular or language versus pipe language, this is what we refer to as a tube cap, which is basically a blind body. And a tube cap is used to seal off the end of an unused tube in a system. So whether this is single ferrule or double ferrule, it's the same thing. You would insert the tube in tight against the shoulder of the fitting. hold the body hex with a wrench and tighten the nut 1 1/4 turns to seal off this tube right here, whether it's been disconnected and you no longer need it, or what the purpose may be. But this is a tube cap for sealing off the end of a tube. Okay, a tube plug is the biggest confusion, because in actuality it looks like a pipe cap, but in our language, in the tubing world, it's a plug, and the tube plug is used to close off an unused tube port. Maybe you have a T in a line, and for whatever reason you disconnect the branch port of the T and you're no longer going to use that line, but you need to keep the run at play in the tube line across from one end to the other. And so you just take this plug, screw it onto that unused port to the finger tight position, and with the proper wrenches you would tighten that plug 1/4 of a turn, and that would seal off that port and allow that T or that unused branch line to be available if you wanted to reconnect in the future. So again, we plug a port and we cap a tube. That's the verbiage that is used in our industry. Again, we cap a tube and we plug a port. So that'll help if that confuses anybody.
Hey, Ron.
Yes.
Sorry to interrupt. Just a quick question, or maybe more of a point of clarification on the pressure rating chart that you showed a couple of slides earlier. Before we get too far past it, maybe you can work back. So just I guess to clarify, so the tube fittings that you'd be using alongside a tubing in a particular OD and wall thickness. So the tube fitting itself is designed to meet the maximum possible working pressure that the tubing it's coupled with is rated to. Is that correct?
Okay, that's an excellent question. We get the question all the time of what pressure rating is your fitting rated to? And the way to answer that is simply this. Our fitting is rated to the working pressure of the tube and will hold to the burst of the tube when properly installed in accordance with manufacturer's instructions. But to rate the tube's the fittings pressure depends on the connection ports on that configuration. So let's say you've got a 1/2 inch tube by 1/2 inch female Npt straight female thread connector. Even though the compression side would be rated to 6,200 PSI with a 4-to-1 safety factor, the lower rated end connection would be the 1/2 inch female Npt. So you have to rate the fittings capability to the lowest end connections pressure rating. Again, if you had a male elbow with an SAE positionable thread on it with an O-ring seal, the compression end would still be rated in 1/2 inch maximum wall to 6,200 PSI at 083, but the male SAE port that's on the other end of the elbow with the O-ring seal may only be rated to 4,200 PSI or so, as an example. So the fitting itself is always rated to the lowest pressure rated connection on that configuration. Does that explain that pretty well?
Yeah, I think that was a great explanation. I'll let you know if there's any follow-up. There is actually a related question that just came in. So can you comment on, or I guess speak towards how bending or temperature impacts this tube rating? Is there I guess a temperature derating chart or anything that speaks to how bending might affect its pressure?
Oh, absolutely. Yeah, there's definitely charts that give you the working pressures or derates based as the temperature rises, and that's based on the natural characteristics of stainless steel, which is what we're talking about here. So these pressure ratings right here are at ambient, and they would definitely go down as temperature increases. Bending does not affect this in any way other than temperature. Now, obviously, if you bend a piece of tube and you deform it in any way, you work harden it in that area, and it will be much harder than it is in a straight undeformed section. So if you were to take a piece of tube and bend it into a 90 and plug off one end and put it into a burst chamber and pressurize it to burst, I would bet my house that it will always burst in one of the straight legs that have not been deformed versus in the elbow that has been deformed. because of the work hardening process. So elbows or bends in tubing makes the tubing much harder than it originally was in its straight, undeformed state. So it would always rupture in a straight section in a burst test. So again, back to these pressure ratings, a 1/4 inch union T that's got compression all the way around would be rated to 10,200 PSI because all 3 compression ports would be rated to the working pressure of the tube. But as I said earlier, a female branch T that's got compression by 1/4 inch female NPT would be rated to the NPT pressure rating for 1/4 inch female NPT in stainless steel. So the fitting is always rated to the lowest pressure rated end connection on the configuration.
Perfect. Thanks, Ron.
Okay, here's another adapter right here that will make your life much easier. It's called a port connector. It's machined from bar stock. And because it is bar stock, it has the same hardness as the ferrules because they're machined from bar stock as well. So to have the ferrules be able to perform properly on the port connector, on the tube stub side, a simulated groove is machined into the port connector so that the leading edge of the front ferrule will find that groove as a home and it will seat into that, and the front end of the ferrule will stop on that shoulder. But the purpose of a port connector is simply this: it allows you to connect 2 compression ports very close together to save for spacing without going through the frustration of cutting a very short piece of tubing to do so. So the way that you install it, if you go to step number 1, and we're going to connect this valve end to a female elbow over to the far right, you would take the nut and ferrules out of the first port and you would stick the tube stub through the nut so that when you thread the nut onto the fitting port on the valve, the tube stub with the groove is sticking outward. Now the installation for the simulated ferrule end of the port connector is just like the plug that we talked about earlier. You would run the nut down hand tight and then you would tighten the nut 1/4 turn. There's no swaging to take place. You just simply need to create a seal between the simulated ferrule and the body bevel of the tube fitting port. So in step number 2, we've completed that process here where we've inserted the port connector back through the nut and we've tightened a 1/4 turn right here. Now, the second step to this would be to take the next compression port that we're going to connect and slide it onto the port connector tube stub side. And once it's bottomed out, then we'll hold the body of the fitting with a backup wrench and we'll tighten the nut 1 1/4 turns just like a standard tubing connection. And so once you've done so, you've completed this installation and you've connected 2 compression connections very close together with a bar stock port connector that has the pressure rating of the maximum wall in that particular OD size, and you've eliminated the frustration of trying to cut a piece of tube the exact length so that this will work properly between these 2 connections. Okay?
Hey, Ron,
Yes.
can you go back to that real quick?
Okay.
I may have heard you wrong, but machined ferrule end step 3, or the second step 3, I thought you mentioned that would only be needed to turn a 1/4 turn with the wrench.
Number 2 right here is only a 1/4 turn with the simulated ferrule, just
Okay,
like the plug that we talked about earlier in plugging a port.
okay, but if you go down and look at your bullet point number 3, it says 1 1/4 turn, I believe.
That's on the tube stub end. That's for this connection over here.
No, up on the machined ferrule end. Up, go up.
Up.
Right there.
Well, that's a typo.
Okay,
Because
I wanted to confirm that was a typo, so that if we share this later, we'll probably want to correct that. So that's what I wanted.
Thank you for catching that, because I've done this so many times. I haven't even paid attention to that. But the simulated ferrule needs no swaging because it's a machined bar stock component. So that tightening for that simulated ferrule end is only 1/4 turn. It is not 1 1/4 turns.
All right,
you wouldn't be able to accomplish that, especially in stainless. It would probably gall the thread. So that's 1/4 turn installation here, 1 1/4 installation here.
Great, thank you.
I appreciate you catching that. Okay, another problem that you have in the tube fitting world is many times you will install an elbow or a T with your Npt threads, if that's the most common thread used. And once the threads get tight and they seal, the tube port is not aligned with the direction of the tube run that needs to come in to make the connection. So you have a couple of options in this situation right here. You can try to over torque this to make it line up with the tube and run the risk of breaking the forging off into the port, or you can back it out and continue to excessively wrap T-tape over these Npt threads and reinstall it in hopes that this would stop in the right position for you to make this tube connection into the nut and ferrule port. And one way that we can solve that is with a very simple adapter called a tube adapter, which is very similar to the port connector in that it has the same tube stub with the groove on one side of the hex. This particular tube stub adapter is a tube stub by male Npt. So what you would do is T-tape these threads and go ahead and tighten this into the female port. And what that does is creates a opportunity for you to take a tube by tube elbow, slide the elbow down onto the tube stub, and that gives you 360-degree rotation on the tube stub to be able to align the connection of the elbow that you need for your tube run. Go ahead and tighten the tube run connection first by bottoming this tube out, hold the body with the wrench as a backup, and then tighten the nut 1 1/4 turns. And then once you've completed this connection first, then you do the same thing on the tube stub. You hold the body steady, tighten the nut on the tube stub 1 1/4 turns, and you've made 2 connections here with no misalignment and no stress, and you solve this problem right here. Because a lot of times you don't have the luxury of rerouting your tube. That may be the only direction that the tube can come in to connect to this female port right here. And so the tube stub is probably the most versatile connection that there is in the tube fitting configurations for solving problems. Okay, Npt threads, they are dictated by specifications, ANSI and ASME B121 tapered pipe thread spec. For 1 inch and below, most all tube fitting manufacturers cold roll their threads. They do not machine or cut them, so they form them through the use of thread rolling machinery and hydraulic pressure. And it's pretty straightforward. The important thing about cold rolled or Npt threads is that they are formed properly. And the way that Npt threads seal when you mate them together is they seal on the flank. This would be considered the crest, which I call the mountaintop. This is the root, which I call the valley. And this is the flank, which I call the slope. And so as long as Npt threads are made to spec, and the specification calls for the mountaintop or the crest to be truncated off flat, and for the valley to also be truncated off flat, then Npt threads typically don't give you any problem because they seal by interference with each other on the flanks. If you don't have truncated threads properly, those little tips, if they get too pointed, will hit into the valley of the mating thread, and those little thin tips in stainless steel will heat up quickly, and that port will gall immediately. So stainless steel is a little finicky, and so it's really important that high quality threads be produced on compression fittings by being properly formed so that you don't have galling issues whatsoever. Okay, why do people use tubing? There are several reasons. The strength to weight ratio compared to pipe, tubing is much lighter. It's easier to work with. It has high pressure capability. It's readily available. The other thing is, even through 2 inch, you can bend it. You have minimal turbulence because there's smooth radiuses in the bends rather than abrupt piping 90s that cause pressure drop. And the flexibility of the system, you can adapt with Teflon braided hoses with tube stub ends and go right into a tube T and a tube system and go to a hose real easily. You have fewer leak points, and then you always have maintenance. You can make and break and disconnect on every nut and ferrule connection in the system and be able to access the system and do whatever you need to do from a maintenance standpoint. But back to the comparison to pipe. Here's an example here, and this piping comparison here actually shows a sweeping 90 rather than an abrupt 90. I wish I had an abrupt 90 in this picture, because that would further emphasize that when you have abrupt 90s in a piping system, those abrupt 90s cause pressure drop. These sweeping elbows don't tend to cause the pressure drop, but the tube is, you can bend it and not have to use so many fittings and have so many leak points. But if, let's say if this was a welded system versus tubing, you would have to have a burn permit, you'd have to have a skilled welder. In some cases, you have to have x-ray. Then you sometimes have to do flushing. You have to do all types of things if this were a welded system. So in small bore piping systems, and because we have tubing and tube fittings available to 2-inch, our larger fittings, 1-inch and above, are great cost savings alternatives to small bore piping systems that are welded or even threaded for that matter. Because you can just, if you can bend conduit, you can bend tubing and run tubing, and tubing is much easier to field route anyway. So there's a lot of advantages in using tubing versus pipe, especially in small bore piping systems. When you're selecting the proper tubing, you have to take a couple of things into consideration. The proper material. Stainless steel by far is the most common material that we deal with. Then you have to consider the size, the wall thickness for your pressure requirements. And then every manufacturer lists suggested ordering information for the material that you may be considering. For stainless steel, it's fully annealed, 304 or 316 seamless, A269 or A213. And you always want to make sure that it's free of scratches, flat spots. And then everybody recommends RB80 or less, not because the fitting won't work above RB80. Most manufacturers will state that their fitting will work to RB90, but the reason that we recommend RB80 or less is simply from workability, to be able to bend the tube and work with the tube to create your systems. It just makes it easier if it's RB80 or less from a fabrication standpoint. One thing that I'll mention here before I leave this slide, there is no problem with using welded tubing with compression fittings, so long as the welded tube is welded and drawn. And what I mean by that, so long as there's no weld bead or no seam on the tube that would cause it not to be 360-degree circumferentially round, because round ferrules can't seal on out of round tube, or they can't seal on tube that has a weld bead that is not drawn out to keep it perfectly round and concentric. The other thing you need to consider with tubing is not pipe. In other words, it cannot take the abuse that pipe can take. You need to be very careful to protect the OD of the tube, such as you see here, dragging it off of some type of rack, letting it hit the ground, laying it on gravel or concrete or slag on a construction site, letting forklifts or anything else run over it. At all times, you need to protect the OD of the tube, because that's where the ferrules seal. And if there's a deep scratch right in the area where the ferrules may be sealing, then you would have a leak point that is not any fault of the fitting itself, such as this right here. I mean, I've been on many construction sites over the years, and I've kind of laughed and been surprised at how a fitting could perform leak tight on some of the things I've actually seen in the field. So again, while it has many advantages over pipe, it is not pipe, and it cannot take the abuse that pipe can take. Tube end preparation. It's very important that we prepare the end of the tube properly, whether you do that before you bend it or after you bend it. But the basics for tube preparation is to cut it as squarely as possible. The most common method out there, of course, is a hand tube cutter. There are other methods. And then once you've cut the tube, or even during your tube cutting, don't be too aggressive with the tube cutting wheel, because even though we call it a tube cutter, it does not cut or remove any metal at all. It simply separates and divides the metal on either side of the wheel as it travels 360 degrees around the OD. So don't be too aggressive. Tighten the handle on the tube cutter about 1/8 of a turn. Make a couple of rounds to make sure you've made the cut for that adjustment. Snug the handle on the tube cutter another 1/8 to a quarter turn, 2 or 3 more rounds to make sure that you've maximized the cut for that adjustment, and just take your time and not get too quick or too rushed in cutting the tube. Here's some photographs here of the different methods that have been used to cut tubing: a tube cutter, a porter band, an electric saw, and even you can use a hacksaw with a hacksaw guide to try to get it as square as possible. But in all cases, no matter what method you use to cut the tube, you need to always deburr the ID and the OD of the tube. And the reason for that is because burrs, whether they're on the ID or the OD, they can flake off, go downstream, they can stop up very small orifices, or they can damage very sensitive equipment. And so here's several ways of deburring tubing. You can see an example here of a piece of tube that was obviously cut with some type of method other than a tube cutter, because it's got that big pigtail right there on the end that needs to be removed. And so you can use various types of deburring tools here. I would caution you about this particular method right here being installed in the end of a power drill, because if you get too aggressive in driving this into the ID of the tube, you can actually bevel and change the entire shape of the end of this tube. And you need that to be good and flat, and you need the full wall thickness so that that tube will dead stop into the shoulder of the fitting. And the ferrules have a stationary target during pull-up so that they deliver their maximum sealing and gripping action as designed to do so. Okay, we've been talking about the installation of the tube fitting, and we've talked about tube prep. Again, the basics are: once you've prepared your tube, cut it off square, deburr the ID and the OD. You need to insert the tube in tight against the shoulder of the fitting to make sure that it bottoms out fully. Then mark the nut. After you have tightened the nut to the finger or hand tight position, mark the nut with a visual aid, and a Sharpie is a tube fitter's best friend, for a visual reference for 1 1/4 turn pull-up. Using a wrench, you need to hold the fitting body steady with a backup wrench and tighten on the nut only. And if you were installing a union in a tray and connecting 2 tubes together, you need to hold the center body hex of the union and tighten one end of the union at a time. Do not tighten each end, because you need that body to be steady, and you need the nut to travel specifically 1 1/4 turns for proper pull-up. And so right here, let me turn my laser pointer off, and I will play you a little video here that will show you the assembly. We've inserted the tube in. We've tightened the nut down hand tight. We're going to mark the tube for a visual reference so that we can keep track of the number of turns. Now, he marked the tube. You can do that if you like. Basically, the nut is the important thing right here, because the tube will remain perfectly still during the pull-up. And then, of course, you want to watch that mark go a complete 360 degrees for 1 revolution. And then once you've made the full 1 revolution, you want to continue on another 90 degrees for 1 1/4 turn pull-up. And once you've gotten to 1 1/4 turn pull-up, you can then use the no-go gauge and insert it between the nut and the shoulder of the fitting to check for proper tightening. If that gauge will stick or it would go in slightly, you need to snug that nut just a little bit to prevent the gauge from going in. Okay. All right. Another feature that is available on some manufacturers' fittings, I don't know that all of them do this, but we and a couple of more that I do know of provide stop collars on their fittings. What the stop collars will do is eliminate all the guesswork in the installation of the fitting as far as tightening the nut is concerned. Here is a picture of the stop collars themselves. The way you would install the fitting with the stop collar is you would insert the tube in tight against the shoulder of the fitting. There's no need to mark the nut. You would simply tighten the nut until it dead stopped that stop collar, and you could not rotate that stop collar with your finger. At that point, you're at 1 1/4 turn pull up. You cannot over tighten the connection, nor will the connection be under tightened at that point. Now, this is an additional cost to the fitting, but it can do a couple of things for you. It can take all the guesswork out of installation. It can speed up productivity for making tube connections, and it can prevent the other things that I mentioned, over tightening and under tightening. When you go to disconnect a connection that has a stop collar on it, it is very important that you understand that for remake of that connection, you need to remove the stop collar from the fitting port before you insert the pre-swaged nut and ferrules back into that port for reconnecting. The nut always needs the freedom to travel some fraction past the initial stopping point to complete the installation, and if the stop collar is still on the fitting body, it cannot do so. For our larger sizes, 1 1/4, 1.5 inch, and 2 inch, it is a requirement that you use a hydraulic or an electronic pre-swaging tool to preset the large, bulky ferrules and nut onto the tube. Once you've done that, you take your tube with the preset nut and ferrule system, you mate it with the body of the fitting, tighten the nut down hand tight, and then with wrenches, you would hand tighten the nut 3/4 of a turn to complete the installation. The hydraulic and electronic swaging tool is not limited strictly to the larger OD sizes. There are jigs and dies from 1/2 inch all the way through 2 inch. So if you're in a situation of high production in smaller sizes, you could use either one of these tools to speed up that process and to assure proper installation and take a lot of the heavy work out of it, especially if you're using maximum wall tubing in those applications. Okay, we're pushing for time, and I'm trying to rush here. Let's talk about some tube bending real quick. When you're bending tube, the 3 things that are very important: measure exactly, bend as accurately as possible, and always use the center line for your measuring, the center line of the tube, that is, from point to point. There are 2 ways that typically people will measure. Some people will start at one end of the tube and they will mark all of the bends on that tube and cut it off, and then they'll bend every mark. Those are very experienced fitters. I have seen guys on construction jobs, especially in a pulp and paper mill, where they're running lube lines from one floor to another, take a piece of wire or clothes hanger or a paper clip and just simply bend that piece of wire or clothes hanger into the exact shape of what the tube has got to look like to connect these 2 terminal points, and then make all of their measurements, mark that tube off, and then bend it exactly in the shape of that preformed wire, and then stick it right up through that paper machine floor, and it fit perfectly. So again, it's an art. The other way to do it is to mark and measure, and then measure from that bend to the next bend, mark that one, and then bend that one. So it depends on the guy that's doing the bending as to what he's most comfortable with based on his experience level. Those are the 2 methods that typically take place. There are 4 things that are important to tube bending: a reference mark, which you need to identify as which end of the tube you started from. So you need to always identify the reference mark. The second one is a measurement/bend mark. That's where you would mark the tube for where that bend needs to take place. The next would be a directional mark. The directional mark will allow you to keep up with which direction you need to make the bend in. So the directional mark goes on the top of the tube once you insert the tube into the hand bender, so that you keep up with the direction of the mark. And then the last mark, of course, is the terminal cutoff mark. One of the things you have to deal with in bending tubing is gain. When you bend a 90-degree bend in tubing, that is a sweeping elbow rather than an abrupt 90-degree acute angle, the tubing grows in the direction of the bend. So if you have no bends prior to the first mark and you're going to bend a 90-degree bend, there is no consideration for the gain. But if there's any bends prior to the next mark on the tube, based on the degree of bend, when you make that next mark, you have to adjust out the gain at that point. And typically, it's about an OD gain. So if you bend a 90-degree bend for 1/4 inch, the gain will be about 1/4 inch. Same for 3/8 and same for half. For 90-degree bends, for a 45, it would be half of that. It'd be 1/8 in 1/4 inch, and so on. So we have to adjust for gain. Here's the reference mark I referred to. You'd want to ID which end of the tube you started in making your measurements. The measurement or bend mark is where you would actually be making your bend. And so when you insert the tube into the bender, you would align this measurement mark onto the 45 for a 45-degree bend, or you would align it onto the R if your reference point is to the right of the bender, or you would put it under the L if your reference point is to the left of the bender. And in most cases, people feed the tube to the left. So the most common alignment would be for this measurement mark to be under the L. Sometimes when you're bending 90s back to back, you may not be able to continue to feed to the left, and you have to flip the tube around in order to be able to make the next bend. And that would be when you would make the measurement mark under the R, because your reference mark or the end of the tube that you started from has now been moved to the right hand of the bender. In a 45, it's not going to matter which side of the bender that the reference mark or the beginning point of the tube is, because you're going 45 degrees. The directional mark, of course, is a longitudinal mark over the measurement mark that would tell you, I need to bend this bend straight down from where this measurement mark is so that my 90-degree bend will be in the proper plane. So that's what the alignment mark is for. And then, of course, the terminal cutoff point. Always try to bend in the same direction, although it a lot of times is not possible. And typically the common practice is to feed the tube to the left and align your marks and then make your bend. Again, here's the alignment mark for the bend, and on the right hand side you see where you need to align your measurement marks based on what the angle you're bending and where the reference point is located in relationship to the bender. Bend accurately and be sure to allow for spring back. So if we're bending to a 90-degree angle, bend specifically to 90, and then when you take the pressure off the bender, you're going to see that bottom leg, that vertical leg, you're going to see it spring back 3 to 4 degrees. So you're going to have to make sure that you adjust for that spring back, and you need to do that very carefully and in increments. Do not overbend, because that 90-degree section where we've bent that tube now is much harder than it was originally, and it doesn't deform well a second time, and it'll be very hard for you to straighten that bend out so that your connections will work out properly. Again, don't overbend. Then after you've bent the tube, you can verify the bend angle using a tape or a ruler. There's a lot of tools for you to check your accuracy. Proper routing of the bends. On the left, you would see a situation that you do not want to do, because it's very difficult to cut a straight length of tube that would bottom out in both connections. And if one end of this is not free for you to slide that nut and ferrule and fitting onto that straight tube anyway, it'd be very difficult to even make this connection at all. This would be the proper way to make this connection so that you have access for maintenance going down the road. And again, same thing here, no straight sections. Take advantage of an expansion loop to allow access for maintenance. And again, instead of this, we want to use what I call a jumper. And again, this is critical for bending. If you miss the center line dimension from this port straight across to this port, If you're short, then your legs are going to be this way. And that's going to be hard for you to get the tube into these ports. If you are overshot on this distance, now your legs are going to be angled inward and you may not be able to bottom the tube out. So again, measuring it accurately and bending accurately is very important. Again, here, you don't want to run tubes over things that you need access to, such as this right here. You want to just use some common sense. Here's a panel with a bunch of lines right here. You can see that they've kind of staggered these unions so that they can get back in and do maintenance and have access to these unions with wrenches. This would be an example of tube runs in a tube tray. You use expansion loops to raise the unions up out of the tube run. So again, access for maintenance with your wrenches going down the road. Proper tube support. There are all kinds of ways to support tubing. These are the polyethylene halves with the stainless brackets, plates, and bolts here to support the tube properly. There's single line clamps, there's double line clamps, there's gang clamps, there's all types of ways to properly support your tube. And then the proper support distances for each OD size is listed here. 1/4 through 1/2 every 3 feet, 3/4 through 7/8 every 4 feet, 1 inch every 5 feet, and then 1 1/4 and up every 7 feet. So we've made it, and that concludes my portion of the presentation, and I appreciate your time and attendance.
Thanks, Ron. That was great. Lots of good information. We do actually have one question sitting in the queue right now. It kind of takes us back all the way to the discussion of the port connector. So I don't know if you can rifle your way back to that slide, but and I will remind everyone else that's in attendance still that you feel please continue to send your questions in if there's anything else that's on your mind. We'll be around for another couple of minutes. But so regarding this fitting, Ron, the question was, so it's shown here that the valve is connected to the elbow here using this port connector tube stub. Is there a way that this can be done without the tube stub end and sort of go directly into the 90-degree fitting, or alternatively, are there valves themselves that have a 90-degree end connection?
Yes, the answer to that question is yes, because we would make, we would make this elbow with a tube stub itself on it, sticking to the left. So then you would take the tube stub on the elbow and insert it into this nut and ferrule connection on this valve and make one connection.
Got it. Okay. Perfect.
So you can
I think that's
with tube stub by female NPT and accomplish that.
okay. Perfect. Yeah, I think that's exactly the answer that we were looking for. But I'll let you know if there's any follow-up. So that's all the questions we have in the queue right now. So I'm gonna turn this over to Kevin to sort of get us wrapped up. And yeah, here you go, Kev.
Thanks, Ron. That was really great information. Who knew we'd be going an hour on that, but it was a lot of great information, like Dan said. We appreciate your efforts today, Ron and Andy. Thanks for being with us, and everyone out there in attendance. Thank you again. Just real quick, some things that you can, if you're interested in seeing any of the DK-LOK product line, you can go to our website where you can download drawings, 3D drawings, 3D animations in any format you wish. And as far as next week goes, oh, I forgot to say, we can also issue your certificate of completion if it's something that your company would like to see you get, or if you would just like to hang something else on your wall. Finally, next week, we are going to have Aegis Flow Technologies with us to talk about Teflon inline valves, and they will get into a great deal of the chemistry behind the different fluoropolymers available. So that will be next week, Wednesday, October 21st. And again, as a reminder, our past recordings are on our website, as this one will be here later on today or tomorrow. And we do have a catalog of any day one-on-one tailored training available as well. And finally, at the conclusion of this, you will get a survey. And I will say that this topic came out of some suggestions from some of our attendees. So we do value your opinions. We'd like to know how we're doing so we can keep doing it, or if it's not good, do less of it. So thanks again, and have a great week, everybody. Bye now.